We will continue with pinhole and how it actually used for knot reversal, for stun and turn. But first, let me just scroll this up. Pinholes and hole punching. As discussed previously, a knot typically includes both traffic rewriting and filtering capabilities. When a knot mapping is established, traffic for a particular application is usually permitted to traverse the knot in both directions. Such mappings are narrow. They usually apply only to a single application for its duration of execution. These types of mappings are called pinholes. So the normal TCP session are only for application and only for session, which is called pinholes, because they are designed to permit a certain temporary traffic flow, i.e. a pair of IP address and port number combinations. Pinholes are usually established and removed dynamically as a consequence of communication between programs. A method that attempts to allow two or more systems, each behind a NAT, to communicate directly using pinholes is called hole punching. So a hole punching is how you traverse a NAT, or it's a method that attempt for direct communication for a host behind the NAT. To punch a hole, a client contacts a known server using an outgoing connection that establishes a mapping in its local NAT. When another client contacts the same server, the server has connections to each other of the clients and knows their external addressing information. So basically, they will contact that server and they will save, or that server will save their information, therefore will be able to relay to each clients their respective addresses. It then exchanges the client external addressing information between the clients. Once this information is known, a client can attempt a direct connection to the clients. The popular Skype peer-to-peer application uses this approach and some others. Referring to figure, assume client A contacts server S1 followed by client B. S1 will have learned A's and B's external addressing information, IPv4 addresses 192.0.2.201 and 203.0.113.100 respectively. By sending B's information to A and vice versa, A can attempt to contact B directly at its external address and vice versa. Whether this will work depends on the type of NATs that have been deployed. NAT state for the A, S1 connection lives in N1, and NAT state for B, S1 lives in both N2 and N3. So for the B is actually nested NAT, or on the right side of this diagram. If all NATs are endpoint independent, this is sufficient for connections to be possible. Any other type of NAT will not accept traffic from other than S1 and will thus prohibit direct communication. Said another way, this approach fails if both hosts are behind NATs with address dependent or address and port dependent mapping behavior. Unilateral self-address fixing, UNSAP. Applications employ a number of methods to determine the addresses their traffic will use when passed through a NAT. This is called fixing, learning and maintaining the addressing information. There are indirect and direct methods for address fixing. The indirect methods involve inferring NOT's behavior by exchanging traffic through NOT. The direct methods involve a direct conversation between the application and the NOT itself using one or more special protocols that are not currently IETF standards. Considerable effort within IETF has gone into the development of the indirect methods, and they are widely used in certain applications, with VoIP applications being the most popular. An application attempting to fix its address without help from the NOT performs the address fixing in a so-called unilateral fashion. Applications that do so are said to perform unilateral self-addressing (UNSAF). As the name suggests, such methods are considered to be undesirable in the long run but a necessary evil for the time being. UNSAF involves a set of heuristics and is not guaranteed to work in all cases, especially because NOT behaviors vary significantly based on vendor and particular circumstance. In most cases of interest, UNSAF methods operate in a client-to-server fashion, similar to hole punching, but with added generality. So it's still one of the properties it is similar to with hole punching, which traversing through the NOT is with added generality. It's similar to hole punching but with just added generality. Figure 7.7 illustrates some of the hazards that can arise in this situation. One issue is the lack of a single outside address realm for every NOT. In this example, there are two levels of NOT between client B and server S1. This situation can cause complications. For example, if an application on B wishes to obtain its outside address by using UNSAF with the server, it receives different answers depending on whether it contacts server S1 or S2. Finally, because UNSAF uses servers that distinct from NOTs, there is always the possibility that NOT behavior reported will change over time or become inconsistent with what the UNSAF approach reports. So here, applications running on clients behind the NOT may require a help from a server to engage in direct communication. In hole punching, a server, often specialized for a specific application, provides rendezvous information among clients that first establish NOT state and then perform direct communication, if possible. Some applications attempt to fix, determine, and maintain the addresses and port numbers their traffic will be assigned when passing through a NOT using standard generic protocols. So this is the UNSAF, where it tries to fix and determine and maintain the addresses and port numbers their traffic will be assigned when passing through a NOT using standard generic protocols. These methods may encounter troubles in certain situations, such as environments with multiple levels of NOT. In this example, client A's external address visible as S1 is 192.0.201 and client B's is 203.0.113.100. At S2, however, B's external address is 10.0.1.1. Given the various problems with NOTs and UNSAF, the IAEB, an elected group of architectural advisors within the IETF, has indicated that UNSAF protocol proposals must include responses to the concerns in their specifications. First, define a limited scope problem that the short-term UNSAF proposal addresses. Second, define an exit strategy or transition plan. Third, discuss what design decisions make the approach brittle. Fourth, identify requirements for long-term, sound technical solutions. Fifth, discuss any noted practical issues or experiences known. Despite all the aforementioned problem, UNSAF methods are commonly used, partly because a wide range of nuts are found in operation today with little consistent behavior. We now look at how these methods are used as building blocks to form robust, general-purpose nut reversal techniques to maximize the chances that communication among systems behind nuts, even between systems across multiple nuts such as the one illustrated in Figure 7.7, will be possible. So again, UNSAF is where when applications employ a number of methods to determine the addresses their traffic will use when passed through a nut. So when traversing through the nut, like here with A to B, this is called fixing or learning and maintaining the addressing information. So there are indirect and direct methods for address fixing. The indirect methods involve inferring nut's behavior by exchanging traffic through the nut. The direct method involves a direct conversation between the application and the nut itself using one or more specialized protocols. Considerable effort within IETF has gone into the development of indirect methods, and they are widely supported in certain applications, with VoIP applications being the most popular. An application attempting to fix its address without help from the nut performs the address fixing in a so-called unilateral fashion. So trying to learn the nut, kind of like the nut traversal of Stan, which we will discuss later. Without the help of the nut, you're gonna talk with a peer-to-peer client. So you need to have some mapping established there using some servers. Applications that do so are said to perform unilateral self-addressing, which is learning it from the application directly. As the name suggests, such methods are considered to be undesirable in the long run but a necessary evil for the time being. UNSAF involves a set of heuristics and not guaranteed to work in most cases. So it works in a client to server rather than P2P, which we will discuss later in Stan. So here we go. Session traversal utilities for NAT Stan. One of the primary workhorses for UNSAF and NAT traversal is called Session Traversal Utilities for NAT Stan. Stan has evolved from a previous version called Simple Tunneling of UDP through NATs, now known as Classic Stan. Classic Stan has been used with VoIP or SIP applications for some time, but has been revised to be a tool that can be used by other protocols for performing NAT traversal. So initially it was used for VoIP or voice over IP call and SIP applications, the classic Stan, but then revised to be a tool for NAT traversal. So this Stan is actually is a previous version of simple tunneling of UDP through NATs. Applications requiring a complete solution for NAT traversal are recommended to begin with other mechanism we discussed in 7.4.5, which is ICE and SIP outbound. So if you want a complete solution, you need ICE, which we will discuss in the next video. So that is more comprehensive. It's not like Stan. Stan kind of its basic protocol or where ICE came from, but for itself, it's actually not enough. Kind of like it's the JavaScript, but it's not the Angular, React, or Vue that provides the functionality. These frameworks may make use of stun in one or more particular ways called stun usages. Usages may extend the set of basic stun operations, message types, or error codes defined in RFC 5389. So ICE could use stun, like we discussed in the previous video, as a fallback from hole punching, or it could be used for other application as well called stun usage. Usages may extend the set of basic stun operations. Just like ICE, it extend the stun operation. Turn as well extend the stun operation. Message types or error codes defined in RFC 5389. As we will discuss in the future video, they will add attributes, message types, and error codes to extend its functionality. Stun is a relatively simple client-to-server protocol, so it's not P2P, that is able to ascertain the external IP address and port number being used on a NAT in most circumstances. It can also keep NAT bindings current by using keep alive messages. So it's a client to server, it used keep alive, and it used to ascertain or to know the external IP and port numbers it is trying to communicate. It requires a cooperating server on the other side of the NAT to be effective, and several public stun servers are configured with globally reachable IP addresses and are available for use on the internet. The main job of a stun server is to echo back stun requests sent to it in a way that allows the client addressing information to be fixed. So it needs a server on the other side of a NAT from where the private hosts are sending information, and several public stun servers are configured with publicly, or it can be reachable from the internet. So this server will echo back stun requests sent to it in a way that allows the client addressing information to be fixed. So that client address information, it will fix it there, or it will map it to be able to use kind of like in hole punching for relaying it to others. As with unsoft methods in general, the approach is not foolproof. However, the attraction of stun is that it does not require modification of network routers, application protocols, or servers. So the good thing about this is that the application can use this without actually trying to change the protocol on the router. So the router just see UDP and TCP, and it just manipulated through its globally routable server. It requires only that clients implement the stun request protocol and that at least one stun server be available in appropriate location. Stun was envisioned as temporary measure, as were many standard protocols now in widespread use a decade or more after their creation, until a more sophisticated direct protocol was developed and implemented, or NATs became obsolete because of the adoption of IPv6. Stun operates using UDP, TCP, or TCP with Transferred Layer Security, TLS, see Chapter 18. Stun usage specification defined which transport protocols are supported for the particular usage. So the stun usage really depends on the protocol, whether it's TLS, TCP with TLS, TCP, or UDP. Those are different kind of stun usage. It uses port 3478 for UDP and TCP and 3479 for TCP or TLS. In the next future video, we will discuss how a same port number could be used for different protocols such as UDP and TCP. So you're kind of like recycling those port numbers and the IP. The STAN-based protocol has two types of transactions: request or response transactions and indication transactions. Indications do not require a response and can be generated by either the client or the server. All messages include the type, length, magic cookie with value 0x2112A442, and a random 96-bit transaction ID used for matching request with response for debugging. So a request requires a response, but an indication do not require a response. Each message begin with 20 bits and may contain 0 or more attributes. STAN message types are defined in the context of methods that support a particular STAN usage. The various STAN parameters, including method and attribute numbers, are maintained by IANA. Attributes have their own types and can vary in length. The basic STAN header, most often located immediately following a UDP transport header in IP packet, is shown in Figure 7.8. Figure 7.8, STAN messages always begin with 20 bits and are usually encapsulated in UDP. Although TCP is allowed, the message type gives both the method, binding, as well as class required response, error, or success. The transaction ID is a random 96-bit number and used to match request with responses or for debugging in the case of indications. Each STAN message can hold 0 or more attributes depending on the particular usage of STAN. So this is kind of like the TLV structure. This is how the STAN header and the STAN data attributes. This is where after the protocol header. So the basic STAN header is 20 bytes in length, see Figure 7.8, and the message length field provides for an entire STAN message length of 216 minus 1 bytes. The 20-byte header length is not included in the message length field, although messages are always padded to a multiple of 4 bytes, so this field always has its two low-order bits set to 0. STAN messages sent over UDP or IP are supported to form IP datagrams less than the path MTU, if known, to avoid fragmentation. So, STAN messages sent over UDP, which is its most or common use, are supposed to form IP datagrams less than the path MTU. So it's always less than the path MTU to be able to avoid fragmentation of the IP fragment. If not known, the entire diagram length, including IP and UDP headers and any options, should be less than 576 bytes for IPv4 or 128 bytes for IPv6. STAN has no provision for cases where a response may exceed the path MTU in the reverse direction. So servers should arrange to use messages of appropriate size. Again, STAN has no provision for cases where a response might exceed path MTU in the reverse direction. So servers should arrange to use message of appropriate size. STAN messages carried over UDP or IP are not reliable, so STAN applications are required to implement their own reliability. So another thing of its property is the server or the stan server are provisioned in such a way that it arranged the IP datagram or not less than the path MTU to avoid fragmentation again. So the request and response avoid fragmentation. This is accomplished by resending messages thought to be lost. So to implement its own reliability, it sends its own keep alive or resending message thought to be lost. The retransmission interval is based on the estimated time to send and receive a message from the peer called the round trip time. So the retransmission interval to send the keep alive is based on the estimated time to send and receive message from the peer or from other stan server and from the peer near to the actual destination called the round trip time. RTT computation and setting retransmission timers will be a major consideration when we discuss TCP in chapter 14. STAN uses a similar approach but with minor modifications to the standard TCP values. CRF C53589. For more details, reliability issues for STAN over TCP over IP or TCP with TLs over IP are handled by TCP. Multiple pending STAN transactions can be supported over TCP-based connections. Multiple pending STAN transactions can be supported base connection means and how it connects to our discussion previously. First, STAN normally uses UDP. Typically, STAN RFC 5389 is client to STAN server using UDP. Very small request or response packets used to discover external IP, external port, not behavior. It usually looks like this. STAN binding request UDP, STAN binding response UDP. Problem: UDP not bindings expire quickly. UDP is stateless, has no handshake, no fin, no keep alive defaults. Not timers for UDP are short, 30 to 120 seconds. This is why STAN keep alives exist. To refresh NAT mappings every 15 to 20 seconds. So that's how the STAN works. It refresh the NAT mappings every 15 to 20 seconds. STAN can also run over TCP. So this NAT mappings also related to the STAN server and its peer. STAN can also run over TCP. RF5389 explicitly allows STAN over TCP, less common but supported. So why run STAN over TCP? Because TCP creates NAT state using SYN or ACK, has long NAT timeout, 2 hours per RFC5382. So it creates a more reliable way. That's why it's a fallback in case UDP didn't work. Doesn't drop fragments easily, supports multiple simultaneous transactions. So STAN can multiplex multiple messages on one TCP connection. Now the quote makes sense. Multiple pending STAN transactions can be supported over TCP-based connection, meaning over UDP, you send one STAN request, wait, get response. If packets reorder or loss happens, NATs get confused. UDP NAT binding may close early. Over TCP, because TCP is ordered, reliable, stream-based, you can send multiple session or multiple requests even before response arrive, because TCP is connection oriented. So TCP will preserve ordering, fragment safely, retransmit automatically, keep the NAT mapping alive, thus multiple pending transactions. So how does this relate to QUIC over UDP? The discussion we have before. QUIC is UDP based but acts like TCP, ordered, reliable, keep its own NAT binding alive, does PMTUD, does retransmission PTO, does handshake. So QUIC behavior is basically transport, UDP reliability, X or not, it's not reliable. Ordering, no. Not lifetime, short, 30 to 120 seconds. Notes, that's the stand default. Transfer TCP reliability, yes, it's reliable. Ordered, yes. Not lifetime, long, 2 hours plus. Notes, stand over TCP are stable. Transport quick over UDP reliability, yes. Quick internal. Ordering, quick stream, yes. Not lifetime, medium, quick keep alive. Notes, it's used for YouTube, FB, or TikTok. So key insight, quick makes UDP behaves more like TCP. Stan over TCP is what quick does but more advanced. How this connects to ICE, stan or turn. ICE uses UDP stan primary. So the ICE, which are the more holistic solution, actually use this UDP stan, not the UNSAF. TCP over TLS, stan fallback. It's the fallback of ICE. The TCP over TLS if stan fails. Turn relay over UDP or TCP. It also uses turn over TLS, TCP as a last resort. So this is the last resort, the turn over TLS. So first, you have UDP stan. If it didn't work, TCP over TLS, stan fallback. If stan didn't work, turn relay over UDP or TCP. If those didn't work, turn over TLS, TCP as a last resort. When NAT is too strict, CGNAT, symmetric NAT, TCP based stan or turn is used because TCP survives restrictive NATs better. So TCP survive a restricted or nested NAT better than UDP. TCP NAT binding lasts longer. Multiple stan messages can be pipelined. Why this matter in the real world? PH or Converge or Globe or Smart in the Philippines, mobile data, heavy CGNAT, strict NAT. Home fiber, Converge, PLDT, mild to medium, CGNAT. Result, UDP stan often fails. Turnover TCP is used. WebRTC calls really most of the time. Quick still work because it has built-in keep alives. YouTube, FB, TikTok avoid stan entirely, pure quick to client server. Let's connect everything in one diagram. Stan or ICE path selection, it try UDP stan. If not allows direct UDP, P2P best, else try TCP stan. Then if not allows direct TCP P2P, rare, else use turn UDP or TCP. Then fallback is turn over TLS, TCP 443 last fallback. Quick path for YouTube, FB, or TikTok, UDP, quick handshake, client to server, then quick keep alive, refresh NAT every 15 to 20 seconds, then quick PMTUD, avoid fragmentation, quick PTO handles lost, no stan, no ICE, no turn, just client to CDN. So for quick, it actually doesn't use stan or ICE or turn, it's just client to CDN. Finally, final summary, well, multiple pending stan transaction can be supported over TCP connection. It means stan over TCP can handle many simultaneous messages. TCP makes NAT mapping stable. TCP ensures order and transmission. It's used when UDP stan fails due to NAT. Quick-based apps, YouTube, Facebook, TikTok, do not use stan or ICE. It uses UDP with Quick's own handshake, reliability, keep alives. Quick fixes UDP the same way TCP fixes ordering. WebRTC based apps, Zoom, Messenger, Call, Discord. Use stan or turn or ICE heavily. It uses stan over TCP when UDP fails. Use turn relay when both fails. First, client CDN, meaning the one you asked about. When I say just client to CDN, it means you, the viewer, connect directly to Google CDN server, not to another viewer, not to appear, not using stan, not using turn. It's not P2P, it's WebRTC, it's not ICE. It is not WebRTC, it's not ICE. It is simply YouTube app or browser to Google CDN server closest to you. So there's no stan no turn, no eyes, because YouTube is not peer-to-peer. It uses UDP, quick CDN selection, adaptive bitrate, server switches, only server-side logic. If the CDN and the adaptive bitrate fail, so the connection path, your device, your home NAT or CG NAT, to converge PLDT Globe ISP network to Google Global Cache, GGC or YouTube CDN. So pure client to server. If else version, how YouTube Quick works in real world. So here's the actual real world logic that YouTube client use. If your network allows UDP and Quick port 443 over UDP, use Quick handshake to encrypted to stream start. Keep alive every few seconds. Refresh NAT. Use PMTUD to detect MTU. Use PTO retransmission and UDP loss. This is 90% of YouTube sessions worldwide. Else if UDP is blocked, some corporate Wi-Fi, some mobile data APNs, fall back to TCP or TLS on port 443. Use HTTP over 2 streaming. Else if UDP partially works but quick handshake fails, retry quick over IPv6. If fail, use TCP. Else, if fragmented, UDP false MTU checks. Quick uses smaller packets, 1-200 bytes. Avoid fragmentation. This is why YouTube connection often use 1-200 to 1300 byte packets. Else, if network aggressively drops idle NAT bindings, Quick sends NAT keep alives every 20 seconds. Else, worst case scenario, switch CDN host, switch data center, reduce video resolution, retry Quick. Summary, YouTube is not using STAN because there's no peer-to-peer, there's no NAT traversal, only client to CDN servers streaming. STAN exists only for peer-to-peer connections, like WebRTC. How this connect to STAN and STAN header diagram? So, STAN header, it shows magic cookie, transaction ID, STAN message type, binding, allocate, etc. STAN messages begin with 20 bits and are usually encapsulated in UDP, although TCP is also allowed. Means, STAN packets usually sit directly after UDP header. Example structure, IP header to UDP header to STAN header to STAN attributes. This is required because STAN must be readable by NAT devices for NAT discovery and hole punching. How the STAN header relates to Quick? Short answer, it does not relate at all. They are separate worlds. STAN belongs to WebRTC or P2P NAT traversal. Quick belongs to client to server video streaming. Question, uses STAN, WebRTC, Zoom, Meets, Discord? Yes. YouTube Quick? No. Use Turn, WebRTC, Zoom, Meets, Discord? Yes, if not restricts. YouTube Quick? No. Peer-to-peer? WebRTC, Zoom, Meets, Discord? Yes. YouTube Quick? No. Uses Quick, WebRTC, Zoom, Meet, Discord? Rare. YouTube Quick? Yes. Primary transport. Question, needs NAT traversal, WebRTC, Zoom, Meets, Discord? Yes. YouTube Quick? No. Clear contrast, Quick versus STAN. Quick, reliable stream over UDP. Replace TCP. Used in browser, Chrome, YouTube, TikTok, FB. Pure client to server. NAT traversal not needed. Handshake, PMTUD, keep alive are built into Quick. STAN, NAT discovery protocol. Used in WebRTC. Only for peer-to-peer connections. Needs turn fallback. Keep alive is lightweight. Small STAN binding indications. Does not fix UDP reliability. WebRTC SRTP does that. Why the STAN header is placed after the UDP header? Because NAT devices must inspect the STAN message type. They use the STAN binding request or response to detect your reflexive IP and port. STAN is used to open NAT pin holes. Quick does not do NAT traversal, so Quick packets IP to UDP to Quick encrypted. NAT cannot parse. This is why Quick cannot be used for peer-to-peer. Final summary, everything combined. YouTube uses Quick. Traffic is client, CDN only. No STAN, no turn, no eyes. STAN, used to find your external IP or port. Needed for peer-to-peer. Always follows UDP header. Has magic cookie plus transaction ID. How they are related? They only both use UDP but for completely different reasons. Quick, reliable UDP for client-to-server apps. Stun, not traversal for peer-to-peer apps. They do not mix. Yeah, let's continue the stun in the next video because as you can see it's a lot more here. Yeah, stun is very long.